nanohub.org.
Online simulation and more for nanotechnology.
Hello and welcome. My name is Professor Brian Baduris and I'm in the School of Chemical Engineering at Purdue University. First, I want to thank you for being part of the model eliciting activity regarding quantum dots and solar energy conversion. Today what I hope we talk about is how quantum dots can be used in solar energy conversion, especially talking about what are quantum dot solar cells, how can we use quantum dot solar cells to impact the energy landscape, and how can we use this technology in terms of solar energy conversion. And in particular, what I hope we take away from this message is how we can use some of these mathematical models to be built into your model eliciting activity. What we'll walk through today is the principles of quantum dots, and here we show an electron microscopy image, a TEM, a transmission electron microscopy image of quantum dot solar cell devices. Okay, so these are the individual quantum dots. We see that we have a scale bar here that's on the order of nanometers, and that'll be very important when we talk about the quantum effect in these quantum dots. Because of this quantum size, we have very unique optical properties, and here we see different varieties of the same material with different nanoparticle sizes, okay, giving off different emissions of light. And we'll talk about why that is and how that can be correlated to the band gaps of the materials. And finally, we'll talk about how all of these materials can be implemented to make some kind of solar cell. And here, the image you see here is just of a traditional field of silicon-based solar cells, of pure crystalline, large silicon solar cells, but these can be readily transported to the idea of quantum dot-based solar cells. So what is a quantum dot? Well, here's our electron microscopy images again, okay? Here's a series of a whole bunch of quantum dots, right? These are all kind of speckled out there. And here we've zoomed on one intentionally, and it's roughly 5 nanometers in diameter. And you see that roughly 5 nanometers in diameter, you can actually see the lattice fringes associated with the crystal of this material. So a quantum dot is a nanocrystal semiconductor. So it's a nanoparticle that's made out of semiconducting material that has a very regular crystal structure. And you'll see that each one of these have roughly the same size, roughly the same shape, and they can be made in a very easy and solution processable way. So these guys are made in solution. You can go ahead and collect these guys and you can make an ink that looks very much like the ink that would come out of an inkjet printer. And you can print these in a very similar manner to how you print inkjet materials. So these are in a very similar way, even to how you might print newspapers in a roll-to-roll manner. Okay? One question that immediately pops up is, how is this all possible? Okay? How do you get something that usually, a hard metal or a hard semiconductor that you can't dissolve in any kind of solvent, how do you get these guys to be so small so you can synthesize them? And how do you get them in such a manner that you can actually make inks out of them? Well, what you'll notice in all these images is that in between the nanoparticles, there's actually this space. And that space isn't pure vacuum. In fact, what that space is are organic ligands that are attached to the molecule. Okay? There's a cartoon here that kind of represents that a little bit better. The red ball here is the actual semiconducting nanoparticle, and on the outside of it, these green things here are the organic ligands. Okay? And these organic ligands allow the nanoparticle to be stable in solution and be suspended in solution such that you can synthesize these and print these guys. Now, a transmission electron microscope works based on electron density contrast, and something that's a big inorganic semiconductor has a lot of electron density, so it appears bright in these images. And these ligands here are mostly carbon, and these carbons don't have a lot of electron density, so they appear as bright spots. So there's really not a gap here. It's really these little green guys that you can't see interpenetrating each to each other. And that's why the distance in between each one of those nanoparticles is about the same, because it's roughly the length of these ligands, or the way these ligands interpenetrate in between one another. Okay? Some common quantum dot kind of materials that people like to work with are things like cadmium selenide, cadmium sulfide, cadmium telluride, lead sulfide, and lead selenide. Okay? So one thing you'll think about, and one thing that's addressed in the model eliciting activity is, if you think about a lot of those materials, cadmium and lead, those aren't necessarily the most friendly materials to have, and they can have serious pollution effects. So one thing we'll ask you to think about is how can you think about making new materials that might not have these kind of these toxicity effects, and how do you might design your model itself to try to get around this, and how much emphasis do you put on this toxicity? Now, one thing we want to think about when we talk about these materials is where does solar fall in the general energy usage landscape? And this plot from Lawrence Livermore National Laboratory kind of has the answer, okay? So we'll see that we use roughly 98 quads worth of energy in a year back in 2013 in the US, okay? And as one might expect, a lot of that comes from petroleum, coal, natural gas, and only a very small fraction of it, okay? 0.32 quads comes from solar energy. And really the reason this occurs is because of cost, okay? If we can bring the cost down by bringing down the manufacturing and the synthesis of solar panels, then that will rise, because really what we want to do is to have the same energy uses that we have today, same energy consumption we have today, at a lower cost. And if we can do that using these printing techniques to make solar cells less expensive, we really have a way to have an advantage in terms of having clean, secure energy solutions for the United States. Not only do you want to make these solar cells in a cost-effective manner, but you also have to think about where to place them, right? By definition, a solar cell is only all that useful if the sun is around, okay? And in the US, where the sun shines varies depending on where you're at. And you might know this from relative general life skills, is the fact that here in the southwest of the United States especially, there's a lot more sun than, say, in northern Michigan or here around in Purdue in West Lafayette, Indiana, right? And this plot here shows the darker the red, the more average sunlight that the geography sees on a given day. So when you think about where to install solar panels, one design consideration you might think about is how much sun comes down, right? Because the more sun that comes down, the more times that you can absorb that light, and the more you absorb that light, the more electricity you're able to produce, okay? So not only do we have to think about cost, we also have to think about placement and other geographical factors in mind, okay? Now, how does this all work? Well, we know that different wavelengths of light have different energies, right? And across the visible, these are all in meters, so 10 to the negative 7th is 100 nanometers. So here we have 400 nanometers, 500 nanometers, 600 nanometers, and 700 nanometers. So we go all the way from purple to red light. And we know that the energy of that light is equal to h nu, or Planck's constant, times the frequency of that light. And the frequency of the light is just c over lambda, or the speed of light divided by the wavelength of the light. So the energy is hc over lambda. So we see that at higher wavelengths, we have lower energy, and at lower wavelengths, we have higher energy. And we also know that, here's the visible part, we know as we go to lower energy, we have infrared radiation, and at higher energy or lower wavelength, we have UV rays. And if we keep going, we'll see X-rays and gamma rays as well, right? So now we have to think about, what does this matter for solar cells, right? Well, we don't really care whether we absorb visible light, ultraviolet light, infrared light. We just want to absorb as much of the light as possible, right? Because the more of the light we absorb, the higher the efficiency of our device. And why is that? Well, when a solar cell operates, we care about 3 key parameters, okay? In order to understand the efficiency of the device, we need to know what the short circuit current density is, what the open circuit voltage is, and what the fill factor is. So that's the JSC, the VOC, and the fill factor. And we care about the power of the light that comes into the device, okay? So let's look at what all those terms are. So the JSC, the short circuit current density, is the current density at 0 applied bias to our device. Our open circuit voltage is the voltage at which we have 0 current, okay? And our fill factor is a ratio. And the fill factor is the area of the curve between the maximum power point and the short circuit current density times the open circuit voltage, okay? So if we know those values, we can calculate the fill factor. And if we multiply all 3 of those together and divide by the power of light in, that gives us the efficiency, okay? So now we need to think about, not only do we want to think about the wavelength of light, but now we need to know how much of the wavelength of light is coming down. And we generally think about two different kinds of spectrum for that. We talk about AM0 and AM1.5. And what's the difference? Well, AM0, and that's plotted here, you can see has a nice peak, okay, and then comes almost directly down in a decay kind of fashion. On the other hand, AM1.5 comes up and it's not as high, and then it has all these bumps here throughout. Okay? We see dips down to 0 light coming in. We see significant decreases in light coming in. What's the difference? Well, the difference is AM0 is representative of light that's in outer space. Okay? So now we have no atmosphere of the Earth through which to go. Okay? So that's just basically what the sun looks like. If you're in outer space, you see that there's absolutely just a decay and a peak here somewhere around 500 to 600 nanometers. Okay. On the other end of things, we see that we have a much lower intensity, all right, and that's just because we're going to go ahead and have some of the sunlight pass through the atmosphere. But not only that, we see specific dips in our light, right? And those specific dips associate with different kinds of absorptions due to oxygen, water, and other things that are in the atmosphere here. So what we want to do as engineers is try to design solar cells that absorb as much light as possible, right? So what we can see here is we don't care if we really absorb maybe out past 2,000 nanometers because there's not a lot of light there, right? But really, if we can absorb between roughly 300 nanometers to 1,500 nanometers, that's almost all the light that the sun emits. And if we want to collect all that light, we need materials that will absorb there. So you can think about what kind of energy we need to do that. And the way we do that is we think about the band gap of our semiconducting materials. Now, in our model eliciting activity, we learned that the band gap of the quantum dot can be estimated to be the band gap of the bulk material plus these different terms that depend on the radius of the quantum dot, right? And what does this band gap actually mean? Okay. Well, if we think about it, the band gap is the difference between the energy of the valence band, EV, and the band gap of the energy of the conduction band, E sub C. Okay, so that's our band gap energy. And in the first case, we have our bound electrons, which are sitting in the valence band, right? And if we come in with light in section B here, that has energy that's less than the band gap energy, there's not enough energy to promote that electron from the valence band to the conduction band. So the light comes in, but there's not enough to promote it, and if we don't promote it, it's not a free carrier. If it's not a free carrier, it can't contribute to the short circuit current density. Okay? If we come in with energy that's equal to the band gap energy, okay, we'll see that the light can come in and the electron can be promoted up into the valence band, or into the conduction band, and now this electron in the conduction band can run around, it can contribute to the short circuit current density, and it's a useful photon's worth of energy, right? So you say, well, why don't we just keep shrinking the band gap, shrinking the band gap, shrinking the band gap, then we'll absorb all the light, right? Well, if you think about it, if you make the band gap too small, what happens if the energy of the light coming in is bigger than the band gap energy? Sure, you promote that electron up into the conduction band, that's great. But it turns out that it'll relax very quickly right down to the edge of the conduction band. It'll overshoot, in other words. And that extra energy that you've now lost as it settles back down is really lost to other processes, and it's not usefully converted to electrical energy. So there's this trade-off between wanting to absorb all the light but not wanting to waste too much of the light. And because of that, based on the band gap of the material and what light the sun emits, there's actually a theoretical prediction for the efficiency of the solar cell based on what the band gap of the material is. Okay? So not only can you think about what the band gap will be relative to the size for a quantum dot, but you can also think, what's the optimal band gap that I would design it to be as an engineer? Okay? And what we see, this is called the Shockley-Queisser limit. Okay? It says that the efficiency of a material at low band gaps is somewhere around 10%. So at a band gap of 0.5 electron volts, it's something around 10% efficient. And as we increase, based on what the sun shoots out, we find that the optimal band gap is somewhere in this 1.3 to 1.4 kind of region. And we see as we go to higher band gaps, okay, we're starting to not be able to promote as many of the electrons, so we see a decrease in efficiency. And over here, we're promoting a lot of electrons, but they're losing that energy, and that energy is being wasted. Okay, so there's actually a peak in what we would expect. So for a single semiconductor absorber, something around 33% is the thermodynamic limit. Now there are ways around that with advanced designs, but that's kind of where we're shooting at. And you can see that for different materials, we can get pretty darn close to the ultimate limit of what we might expect. So with that, what I've hoped to show you today is that these quantum dots are really readily designable materials. You can tune their size anywhere between 1 nanometers and 4 nanometers in radii. And by tuning that size, you tune the band gap, okay? And if you pick the right materials and look at what their band gap is in the bulk, you can really tune that across that 0.5 to 2 electron volt kind of band gap range. You can process these from solution. You can synthesize these in solution so you can make low-cost economic solar cells. Okay? And if you can make those low-cost economic solar cells and you put them in the right place, they have the chance to compete with other fossil fuel and solar technologies. Finally, what I hope I've showed you also is that not only does it matter the materials you select, but it also matters what kind of radiation comes in. Okay? So we need to think very carefully both of the power of the light coming in and what wavelengths of light are coming in as well. So we need to match our materials to what we're given in terms of the solar cell spectrum and in terms of the power of the sun. Okay? With that, I thank you for your attention. I wish you the best of luck on the MEA, and I'm sure that you'll be able to design a mathematical model that allow you to formulate the best quantum dot mixtures and design the best quantum dot solar cells.